up settling for pretty close. Well, for centuries, mathematicians have faced that exact issue, especially with complex polynomials, anything higher than degree 4 or 5, usually. Traditionally, you'd grab for numerical approximations. They're super useful, sure, but they always come with that little asterisk, right? They're estimates, not the perfect, precise truth.
Precisely. And that's really where Ezouidi's theorem comes in. It completely reframes what we thought was possible. This isn't about getting a slightly better estimate or inching closer. It's a genuinely new method that delivers exact symbolic solutions. For polynomials that, yeah, until now were seen as incredibly tough, maybe even unsolvable using those standard algebraic tools, it's a real paradigm shift.
Okay, right. Let's unpack this. So, our mission in this deep dive is to really get how this theorem works. And to do that, we're going to put it up against a real beast, a 14th degree polynomial, the kind that would make classical methods just, well, give up. This isn't just theory. We're talking a live demonstration, basically, giving you a really clear understanding of what is, frankly, a significant mathematical achievement. So, just picture this equation, okay? Px, and it starts with x to the power of 14. Then there are 13 more terms, all adding up to zero. I mean, it's a monster. Just seeing that degree 14 tells you immediately this isn't your standard quadratic equation from school. It's the kind of problem that, yeah, traditionally makes mathematicians kind of throw up their hands.
Oh, absolutely. This polynomial poses really significant challenges for those classical methods. When you rely on numerical approximation techniques, things like Newton's method, you're essentially generating estimates. And while those estimates are incredibly valuable in many areas, they inherently have this slight fuzziness, right? Rounding errors, tiny inaccuracies, which means you can never actually guarantee a truly exact value. You're always dealing with close enough, not spot on. And what's really interesting here is how Ezouidi's theorem contrasts with some long held beliefs in algebra. You have Abel's theorem, for instance, which is a huge result. It basically said certain polynomials, especially degree 5 or higher, just can't be solved using radicals, expressions involving just arithmetic and roots. It kind of set a boundary on what was algebraically solvable in that classic sense. But Ezouidi's theorem, well, it doesn't break that theorem, but it finds a new pathway. It shows that even polynomials potentially involving radical roots can be solved exactly. It just uses a different kind of algebraic framework. It sort of redefines what solvable means in the exact sense.
And there's a little twist with this specific polynomial, too. Our sources mention that x1 is actually a root, and it appears twice multiplicity, too. It's like a small clue, maybe hinting at some structure, but even knowing that, it's still a massive challenge for any standard approach.
Indeed, it is. But with Ezouidi's theorem, we don't try to force fit it into those old methods. Instead, it systematically tackles the problem. It effectively breaks down the polynomial, solving for the roots symbolically. Think of it as a recursive process. Like imagine a huge, complex jigsaw puzzle. Instead of trying to solve it all at once, recursion sees the big puzzle is made of similar, smaller puzzles. You solve the smallest one, use that solution for the next size up, and repeat until the whole thing is perfectly solved. No guesswork. That's kind of the core idea here, systematically finding exact values. At its heart, the theorem uses this, well, pretty sophisticated formula. It involves things called binomial coefficients to carefully adjust the terms. It effectively raises the polynomial's degree in a very controlled way, uses a base coefficient, and this is key. It keeps referring back to terms calculated earlier in this recursive chain. It's a really meticulously structured algorithm. Every step builds precisely on the last one.
Okay, so for you, the listener, the takeaway here is we're not talking about some messy trial and error thing or just hoping to land close enough. This is deeply structured, a step by step approach that just completely sidesteps the built in limits of both classical algebra and numerical approximation. It's all about finding the absolute, precise, true value of those roots. That's the crucial difference, isn't
It
it?
really is. And here's where the elegance really shows. The first step is expressing the polynomial using these special symbolic coefficients. We call them scalar. These scalar things are then calculated recursively based on the original polynomial's coefficients. And the critical point is every single one is found symbolically. No numbers plugged in prematurely, no approximations at all. Now, what's genuinely remarkable for this specific 14th degree polynomial we're looking at is that when you calculate these symbolic scalar coefficients, a whole bunch of them just evaluate to zero.
Wow.
Yeah, it dramatically simplifies the whole equation. For this particular polynomial, it turns out only two main scalar terms are non-zero. All the others just vanish.
Okay, this is where it gets really wild. And I have to say, this part kind of blew my mind when I first read about it because this incredible result means that massive, complex 14th degree polynomial suddenly collapses into something way, way simpler. that huge equation basically transforms into something that looks like a quadratic equation, x2 plus bx plus c equals 0. But here, the variable isn't just x, it's x raised to the power of 7. Just think about that for a second. A 14th degree problem you couldn't solve suddenly looks like a structure you learned how to handle ages ago.
Exactly right. From this beautifully simplified form, by 7 2 plus some term times by 7 plus another term equals 0, just finding the exact symbolic roots becomes possible. And these aren't decimal approximations. The roots are expressed precisely, often using things like complex exponentials, capturing their true mathematical nature. For instance, you find that x to the power of 7 equals some specific exact algebraic expression might involve a square root, other numbers. And from that, you derive the final roots for x. This whole recursive process, building precision step by step, guarantees every single root is truly exact. No approximation errors creeping in. It's ultimate mathematical clarity, really.
So, okay, let's think about what this means beyond the math itself. The significance of getting exact symbolic roots versus just really good approximations. For someone maybe not deep in pure math, how big a deal is that difference, practically speaking? Is it just about, theoretical purity, or does it actually lead to different results in the real world?
It's definitely both, but the practical side is potentially huge. Numerical methods are fantastic, incredibly accurate for many things, but there's always that tiny bit of fuzziness, that approximation. Think of it like this: a numerical method gives you an incredibly precise blueprint, maybe accurate to a thousandth of an inch, but a symbolic solution gives you the perfect master blueprint, the theoretical ideal itself. And you can prove it. When you get these exact symbolic roots, you can plug them back into the original polynomial, px, and the equation balances perfectly. Px equals exactly 0. You can even use computer algebra systems to verify this symbolically. And the bigger picture here is that this method isn't just some one off trick for this specific polynomial, it's generalizable. It can, in principle, be applied to any high degree polynomial. That's the groundbreaking part.
Right. And for you listening, this isn't just some abstract exercise for mathematicians. This kind of breakthrough, it has direct, potentially powerful uses everywhere. Think about physics, modeling fundamental forces, particle interactions, maybe, or engineering, designing incredibly precise components, complex control systems, even computer science, algorithms needing absolute certainty for things like cryptography or really high fidelity simulations. In all those fields, getting exact symbolic solutions isn't just nice, it can be absolutely crucial for achieving the kind of model precision and accuracy you need. When your simulations or designs demand perfection, well, this is the kind of tool that really changes the game. So, just to recap where we've been today, we started with this seemingly impossible 14th degree polynomial, kind that usually forces you into the world of estimates. But using Ezouidi's theorem, we've walked through how it's possible to systematically find its exact symbolic roots. It overcomes these really long-standing limits of the old methods. It's pretty amazing, really. A testament to finding new ways to think about old problems.
It really is a major step forward in mathematics. It redraws the map of what's considered solvable in a way. We've shown today, at least with this example, how polynomials of potentially any degree can now be approached to find exact solutions, something classical methods just couldn't promise. With Ezouidi's theorem, we now have a tool, a pathway to unlock the exact symbolic roots, no matter how complex the polynomial might seem.
And that leaves us with a really exciting thought, doesn't it? What other mathematical problems, ones we've maybe filed away as unsolvable for ages, what other problems might just be waiting for a new perspective, an innovative approach like Ezouidi's theorem? You have to wonder what unforeseen advances in science and technology could be unlocked if we find more keys like this. What other walls have we built that are just waiting to be dismantled?